we discovered black holes by seeing what cannot be seen. No light, no shape, no direct signal. And yet, science is certain they exist. So what convinced humanity that black holes are real and not just a mistake hidden inside equations? Black holes were not discovered in space. They were discovered on paper. In 1916, Albert Einstein completed the theory of general relativity, a radical idea that described gravity not as a force, but as the curvature of space and time itself. According to this theory, mass does not simply pull objects inward, it bends the very fabric of the universe, shaping how space curves and how time flows. Only months later, Carl Schwarzschild solved Einstein's equations under extremer conditions. His solution revealed something unsettling. If matter were compressed into a region small enough, space and time would collapse inward, forming a boundary beyond which nothing could return, not even light. For the first time, physics encountered the possibility of a one-way region in the universe. That boundary later became known as the Schwarzschild radius. It was not a physical surface, but a mathematical point of no return. Once crossed, the universe offered no path back. At the time, the idea sounded almost absurd. A place where light itself could not escape seemed to contradict intuition and everything scientists believed about reality. Most physicists did not think this described a real object. It was treated as a mathematical curiosity, a strange outcome hidden inside equations rather than something that could exist in nature. There was no telescope that could see it, no experiment that could test it, and no observation that demanded its existence. At this stage, black holes existed only as logic. They were consequences of equations pushed to their limits, not discoveries written across the sky. The universe had not yet spoken. Mathematics had spoken first. If black holes were nothing more than mathematics, what was the first sign that made scientists suspect they might exist in the real universe? The first clues did not come from darkness, but from motion. Astronomers began to notice stars behaving in ways that should not have been possible. Some stars were moving at extreme speeds, tracing tight, rapid orbits around an unseen center. Their paths were precise, repeated, and stable, as if something immensely heavy was holding them in place. According to the laws of gravity, such motion demands mass, and not just any mass, but an enormous one. The faster an object moves in orbit, the stronger the gravitational pull at the center must be. Calculations showed that these stars were circling something far heavier than any known star, packed into a region far smaller than a star cluster. Yet, when astronomers looked directly at the center of these orbits, they saw nothing. No bright star, no glowing gas, no visible object of any kind. The region was dark, silent, and empty to optical telescopes. There was no light being emitted, no reflection, and no ordinary signal that could explain the gravitational grip on the surrounding stars. This was deeply unsettling. In astronomy, mass and light usually go together. Stars shine, gas clouds glow, even dead stars leave traces. But here, gravity was present without light. Something was shaping the motion of stars while remaining completely invisible. For the first time, science was forced to confront the idea of an invisible mass, a presence known only through its gravitational influence. It did not announce itself with brightness or radiation. It revealed itself only by how it controlled the space around it. If black holes could not be seen directly, how did scientists turn these strange stellar motions into precise measurements of something completely invisible? Motion does not lie. Unlike light, it cannot be faked or hidden. By carefully tracking the orbits of stars and measuring their velocities, astronomers were able to calculate the mass of whatever lay at the center of their motion. The mathematics was straightforward. Even if the implications were not, faster orbits meant stronger gravity. And stronger gravity meant more mass concentrated in a smaller region of space. The results were shocking. The central object had a mass millions, and in some cases billions, of times greater than the Sun. Yet this enormous mass was confined to a volume so small that no ordinary object could survive in such a state. No star could remain stable. No cluster of stars could stay bound without tearing itself apart. Some scientists proposed an alternative explanation. Perhaps the invisible mass was not a single object, but a dense cluster of dark stars, dead remnants, or compact objects packed together. This idea, often called a dark star cluster, was taken seriously at first, but it did not survive careful analysis. Such a cluster would be unstable, collapsing or dispersing on timescales far shorter than the age of the galaxy. As observations improved, the constraints became even tighter. The mass had to be enormous, the size had to be tiny, and the object had to be long-lived. One by one, every conventional explanation failed. The data left no room for ordinary matter behaving in ordinary ways. At this point, the black hole was no longer just a theoretical curiosity. It became the only solution that matched the evidence, not because scientists wanted it to be true, but because nothing else could explain what the stars were doing. But if black holes emit no light of their own, why do some of the regions around them shine with extraordinary brightness? Matter does not vanish the moment it approaches a black hole. Instead, it begins a violent spiral. Gas, dust, and stellar debris are pulled inward, flattening into a rotating structure known as an accretion disk. As this material falls closer to the center, gravity forces it to move faster and faster, grinding particles against each other in an extreme cosmic collision. This friction heats the gas to millions of degrees. At such temperatures, the disk does not glow gently like a star. It erupts in high-energy radiation, especially powerful X-rays. These emissions are so intense that they can outshine entire galaxies, even though the region producing them is smaller than our solar system. X-ray telescopes began detecting mysterious sources of light that could not be explained by any known type of star. These sources flickered and fluctuated rapidly, changing brightness over minutes or even seconds. Such rapid variation revealed a crucial clue. Only an object that is both extremely massive and incredibly compact could produce energy on such short timescales. Ordinary stars were ruled out. Neutron stars could explain some cases, but not the most extreme ones. The energy output was too large, the variability too fast, and the inferred mass too great. Something else had to be responsible for these cosmic beacons. For the first time, black holes revealed themselves not through their own light, but through the light of matter being torn apart as it fell in. They could not shine, but they could make the universe around them blaze. If radiation gave us indirect proof, could humanity ever truly see a black hole itself? At the heart of the Milky Way, something invisible commands absolute authority. Astronomers identified a compact radio source known as Sagittarius A star, a point of intense activity buried deep within clouds of dust and gas. Although it emits little visible light, its gravitational influence dominates the entire central region of our galaxy. Over decades, scientists tracked the motion of stars orbiting this unseen center. These stars followed precise paths, some racing through space at thousands of kilometers per second. Their orbits were mapped year after year, revealing complete cycles that left no room for speculation or guesswork. The data was slow to gather, but relentlessly clear. From these stellar motions, astronomers calculated the mass hidden at the center. The result was extraordinary. Roughly 4 million times the mass of the Sun was packed into a region smaller than our solar system. Such density defied every known form of matter. No cluster of stars. No exotic object. No theoretical alternative could remain stable under those conditions. As measurements improved, the constraints tightened even further. The mass could not spread out. The size could not increase. The object had to be both immense and confined, silent and enduring. One by one, competing explanations collapsed under the weight of the evidence. At that moment, the black hole ceased to be a distant theoretical idea. It became a concrete presence at the very center of our galaxy, not hidden in some far-off quasar or ancient universe, but embedded within the Milky Way itself, shaping the motion of stars only a few light years away. Yet even here, the evidence remained indirect. If black holes controlled stars and lit up their surroundings, what finally allowed humanity to capture the shadow of one directly? In 2019, humanity crossed a historic threshold. The Event Horizon Telescope released the first image ever captured of a black hole. It was not taken by a single instrument, but by a planet-sized network of radio telescopes synchronized across the Earth, effectively turning our world into one vast observing eye. What the image showed was not the black hole itself. A black hole emits no light and reflects none. Instead, the image revealed a dark, circular shadow carved into a glowing ring of hot gas. This shadow was created as the black hole bent and trapped light around it, leaving behind a silhouette against the radiant accretion disk. The size and shape of that shadow were measured with extraordinary precision. When scientists compared the image to predictions made by general relativity decades earlier, the match was astonishing. The curvature of the ring, the diameter of the shadow, and the asymmetry of the glow all aligned with what Einstein's equations had foretold. For the first time, mathematics and observation met without contradiction. What had once existed only in theory and indirect evidence now had a visual confirmation. Not a photograph in the ordinary sense, but a direct imprint of gravity itself acting on light. With that image, black holes stepped out of the realm of debate. They were no longer inferred, suspected, or argued into existence. They were observed, measured, and confirmed. The universe had finally allowed us to see the outline of its darkest objects. If black holes can now be imaged, is there another way humanity can detect them without relying on light at all? In 2015, the universe spoke in a new language. Observatories designed to detect gravitational waves recorded a faint but unmistakable signal. It came from the collision of two black holes, spiraling together and merging more than 1 billion years ago. For the first time, humanity detected an event that did not announce itself with light. Gravitational waves are ripples in space and time itself. When massive objects accelerate or collide, they send vibrations outward, stretching and compressing the fabric of the universe as they pass. These waves travel unhindered, carrying information from places light cannot escape and from events light cannot describe. The signal that was detected matched theoretical predictions with stunning accuracy. Its frequency, amplitude, and final ringdown aligned precisely with models of two black holes merging into one. This was not an interpretation. It was a direct imprint of the event written into spacetime itself. Unlike radiation or images, gravitational waves do not rely on matter or light. They cannot be blocked, absorbed, or hidden. Their detection confirmed black holes in the most fundamental way possible, not by what they illuminate, but by how they reshape the universe during their most violent moments. Black holes were no longer just objects to be inferred or imaged. They could be heard. The universe had provided a new sense, and with it, a new kind of certainty. With every line of evidence now converging, one question remained. How deeply do we truly understand black holes, and how much of their nature still lies beyond our reach? Black holes were never discovered by looking directly at them. They were revealed through patience, logic, and an unwavering commitment to evidence. Humanity followed equations before it followed light, trusted motion before images, and listened to space-time itself when vision was no longer enough. From abstract mathematics to stellar orbits, from violent bursts of X-ray radiation to the faint shadow etched against glowing gas, and finally to the tremble of gravitational waves. Each layer of proof locked the existence of black holes more firmly into reality, piece by piece. The universe allowed us to confirm what once seemed impossible. Yet, at the very boundary that defines a black hole, understanding stops. Beyond the event horizon, no signal returns, no observation survives, and no theory has yet crossed without breaking. It remains a region where space and time collapse into mystery, untouched by experiment and unreachable by certainty. In this way, black holes offer more than discovery. They offer perspective. They remind us that science is strongest not when it claims to know everything, but when it has the courage to face what cannot yet be known. They stand as monuments to both human brilliance and human limitation. Sometimes, the greatest discovery is not an answer, but the moment we recognize the edge of our understanding and choose to keep going anyway. If black holes were discovered only through indirect traces and whispered signals across the cosmos, how many other secrets are hiding in plain sight, waiting for a future mind capable of noticing what we cannot yet see?